At a distance of about 150 million kilometers from Earth, there is a star on which almost everything that happens on our planet depends. We see her every day, but ordinary sunlight reveals only a small part of what's happening on the sun's surface. Behind the bright disk lies a completely different world, a world of plasma, magnetic fields, giant flares, and streams of energy that constantly rise from the depths of the star into space. And to see this world, it is not enough to simply point a telescope at the sun. You have to look at it in a light that the human eye can never see. That's exactly what the Solar Dynamics Observatory, NASA's space observatory known as SDO, does. Its Atmospheric Imaging Assembly, or AIA, instrument observes the sun in multiple wavelengths simultaneously. This allows the same solar disk to appear completely different depending on which part of the electromagnetic spectrum we use.
In some ranges, a relatively calm surface appears before us. In others, the sun turns into a boiling structure of hot plasma. Giant arcs rise above the surface. Dark regions occur where the magnetic field penetrates the photosphere. Bright loops outline magnetic field lines, and sometimes entire regions of the sun suddenly flare up and release enormous amounts of energy. These are not photographs of the sun in the usual sense. These are images constructed from radiation of different temperatures and physical processes, and that is why they allow us to look much deeper into the behavior of our star. SDO creates images of the sun with a resolution of up to 4096 by 4096 pixels, while AIA observes it in several ultraviolet and extreme ultraviolet bands. In standard mode, images can be acquired at intervals of just a few seconds.
For the observer, this means more than just incredible detail. This means movement. The sun no longer appears as a motionless yellow disk. It becomes a dynamic system. Over the course of several hours, one can see how magnetic structures move, how plasma flows along invisible magnetic lines, how loops change shape, and how energy gradually accumulates in the star's atmosphere. And the closer we look, the stranger the sun becomes, because its surface is just the beginning. What appears to be the edge of a star is actually part of a vast atmosphere that extends far into space. It is there that some of the most powerful processes in the entire solar system take place. The sun's corona, the outer part of its atmosphere, has a temperature of millions of degrees. This is one of the most mysterious features of our star. The photosphere, which we perceive as the visible surface, is much colder. But above it, the temperature suddenly rises.
Why is the sun's atmosphere so hot? How does energy move from the inner layers of a star to its outer atmosphere? And how does the magnetic field participate in this process? The answers to these questions cannot be obtained simply by looking at the sun in visible light. That is why SDO looks at it in different ranges. For example, the 193 angstrom channel allows one to observe radiation associated with hot coronal plasma, while some other channels show completely different temperature regions of the solar atmosphere. The result is a kind of temperature map. The same area can look completely different when moving from one wavelength to another. And this is one of the main features of SDO observations. We don't just get a prettier picture. We get different physical layers of one star. Where one range contains a nearly empty dark region, another may reveal a complex structure of hot plasma.
Where a normal image reveals little to nothing out of the ordinary, ultraviolet light can reveal a vast system of magnetic loops. And during a flare, a quiet area can transform into one of the brightest objects on the entire solar disk in a matter of minutes. This is especially important because the sun does not remain the same. Its magnetic field is constantly changing. Inside the star, the matter is in a plasma state, and the movement of charged particles is associated with magnetic fields. These fields can twist, stretch, and store energy. When the structure becomes unstable, the stored energy can be released. A solar flare occurs. At this moment, intense radiation is emitted into space, and sometimes huge clouds of plasma spread out from the sun along with it. For the sun itself, this may be just one episode in a continuous stream of activity. For Earth, the consequences could be much more serious. Particle flows and changes in the solar magnetic field can affect near-Earth space, satellites, and communication systems. Therefore, observing the sun is not just an attempt to understand a distant star. It is also a way to monitor space weather. And here, the advantage of SDO becomes especially important. The observatory can observe the sun almost continuously and track its changing structures. NASA notes that AIA acquires images in several EUV bands at a high temporal frequency, allowing it to study the evolution of solar activity in near real time. Each new frame becomes part of a huge sequence. Hundreds, thousands, millions of images. Together, they turn the sun into a moving map. And it is in such sequences that processes become visible that cannot be seen in a single photograph. Slow changes in magnetic structures.
Plasma movement. Emergence of new active regions. Development of solar flares. And sudden bursts of energy. But the most impressive thing happens when these images are sped up. What in reality takes hours begins to happen in a few seconds. The solar surface begins to move. The plasma seems to flow along invisible lines. Giant structures appear and disappear. Bright flashes suddenly appear against the backdrop of a huge disk. And the main thing becomes obvious. The sun is not a calm ball of fire. This is a giant magnetic machine. Its surface is constantly changing. Its atmosphere is in constant motion.
And its magnetic field connects the processes occurring on the sun with the space far beyond the star itself. And all this is happening right now, while the Earth moves in its orbit, while day and night pass above us. For now, we see ordinary sunlight. At a distance of hundreds of millions of kilometers, the plasma continues to move along the magnetic structures of the star. New active regions are emerging. The old ones disappear. And sometimes the sun releases a flare, the energy of which completely changes the appearance of the star for a short time. But SDO reveals something even more surprising. What we call the surface of the sun is not the real boundary.
There is a huge atmosphere above it. And the higher we rise, the more the physics of what is happening changes. There, magnetic fields become the main architect of what is happening. They form loops. They hold the plasma. They connect distant regions of the solar surface. And sometimes, these structures are destroyed. And then, the energy that has been accumulating for a long time gets the opportunity to break out. It is at this moment that the sun shows its true power.
But solar flares are only one part of this picture. The sun is capable of creating structures that are much larger than the Earth itself. Huge loops of hot plasma can rise above the surface and be held by the magnetic field. In some cases, they persist for hours or even days, gradually changing under the influence of plasma motion and magnetic fields. In SDO images, these structures look almost unreal. They bend over the solar disk, forming arcs that can stretch for hundreds of thousands of kilometers. But these are not solid objects. Plasma does not just hang in the air. It moves along magnetic lines, and the structure itself is constantly rebuilt. Sometimes these loops become especially bright, This happens because the hot plasma begins to emit in certain ranges of ultraviolet, which are sensitive to SDO instruments. That is why the transition between different wavelengths is so important. Each channel shows us a different temperature, the second layer of the atmosphere, the second physical process. If you look only at one range, part of the history inevitably remains hidden. But when several ranges are combined, a much more complete picture emerges. We begin to see how energy moves through the solar atmosphere. And here appears one of the biggest mysteries of solar physics. Why is the crown so hot? This may seem paradoxical. Inside the sun is the source of its energy, nuclear fusion, which occurs in the depths of the star. But the temperature of the outer corona reaches millions of degrees, while the visible surface is much colder. Ordinary heat transfer does not explain the whole picture. Therefore, scientists consider several mechanisms related to magnetic fields and plasma movement. One of the possible processes are small and numerous releases of energy, which occur much more often than large flares. Other explanations are related to waves propagating in magnetized plasma. SDO does not provide one simple answer to this problem, but it allows you to observe details without which it is impossible to check similar models. And the higher the observed quality, the more questions arise. For example, small structures can suddenly become brighter. Subtle magnetic loops can appear in areas that previously seemed relatively calm. And some processes occur so quickly that a few minutes of observation can show a complete restructuring of the solar atmosphere. This is especially well visible during active periods. Regions appear on the sun where the magnetic field becomes especially complex. Such areas are called active. It is here that sunspots, flares, and other manifestations of magnetic activity often occur. Sunspots themselves appear dark only because they are colder than the surrounding photosphere. But their dark appearance hides extremely strong magnetic fields. And if such a region is observed in ultraviolet light, its structure becomes completely different. Bright loops may appear around it. The plasma begins to move along the magnetic lines. Areas of increased temperature appear. And sometimes the whole system is suddenly rebuilt. This is one of the moments when a sequence of images becomes much more valuable than a single frame. One picture shows the condition. A series of pictures shows the process. And the process is exactly what is needed to understand the sun, because solar activity is determined not only by the location of the magnetic field. It is also important how it changes over time. The sun rotates. Plasma moves. Different layers of the star rotate at different speeds. These processes gradually deform magnetic fields, and as a result, energy can accumulate in the crown. Sometimes, this leads to magnetic reconnection. During magnetic reconnection, the magnetic field lines are rearranged, and the accumulated energy is transformed into the movement of particles, heat, and radiation. This is one of the key processes associated with solar flares. On SDO images, it can appear as a rapid change in the brightness and structure of the active area. First, a small bright area appears. Then it quickly expands. Magnetic structures begin to change around it. And in a matter of minutes, a quiet area of the sun turns into an extremely active area. But even the most powerful flashes are not always the same. Some are accompanied by a coronal mass ejection.
Others occur without a large-scale ejection of plasma into interplanetary space. This difference is of great importance, because the flare and coronal mass ejection are related but not identical phenomena. The flash is primarily a powerful emission of electromagnetic radiation. A coronal mass ejection is a giant cloud of plasma and magnetic field that may leave the solar corona and travel through the solar system. If such an emission is directed towards the Earth, a completely different story begins. The cloud can spread through interplanetary space at a speed of hundreds or even thousands of kilometers per second. And if it reaches the Earth, the interaction with the magnetosphere of our planet can cause a geomagnetic storm. One of the most famous consequences is the aurora borealis. But behind the beautiful glow of the sky are quite real physical processes. Charged particles interact with the Earth's magnetic field and the atmosphere. Electric currents arise. The state of the upper layers of the atmosphere is changing. And during particularly strong events, space weather can affect the technological infrastructure.
Satellites, navigation systems, radio communication, energy networks. Therefore, SDO images have significance far beyond basic science. They help track the source of space weather. We can see where the active area is formed. We can watch how it develops. We can fix the flash. And we can compare solar events with what is happening in near-Earth space. In this sense, SDO works not only as a camera. This is a system of constant observation of the star, which is located in the center of our planetary system. And the longer the observations continue, the more valuable the archive becomes. The sun goes through cycles of activity. The number of sunspots and the intensity of some of them change over time. Therefore, the multi-year flow of data makes it possible to study the sun not as a single moment, but as a constantly changing system. It is here that another important feature of these observations arises. The sun can look completely different in different periods of its cycle. Quiet years are replaced by more active ones. The number of large active areas varies. The number of flashes increases or decreases. The structure of the crown is changing, and the magnetic field of the star undergoes large-scale changes. Therefore, shots taken in different years may look as if different stars are in front of us, but it's still the same object, the same star, the same surface, just the second phase of her magnetic life. And when such images are combined into one sequence, it becomes noticeable how dynamic the sun is. At first glance, it seems stable, but on a scale of time from seconds to years, its atmosphere is constantly changing. Hot plasma rises. Magnetic loops are formed and destroyed.
Active regions rotate with the sun. Outbreaks occur suddenly, and the energy continues to go into outer space. And all this is happening on a star that determines the conditions for the existence of our planet. But there is another reason why SDO images are so unusual. They allow us to see more than just the shape of the solar atmosphere. They allow you to see its structure in different temperature states. And when these images are superimposed on each other, a multi-layered sun appears. Cold regions, hotter regions, extremely hot crown, magnetic loops, active areas, and the plasma moving between them. This is almost a map of the invisible sun, a picture that cannot be obtained by human vision, because the human eye sees only a very small part of the electromagnetic spectrum. Most of the information carried by solar radiation is invisible to us. SDO extends this range, and that is why the star, which humanity has been watching for thousands of years, suddenly reveals itself from a completely new side. We see her not as she appears from Earth. We see it as it is in different radiation ranges. And the longer SDO observes, the larger this invisible archive becomes. Each frame captures the state of the sun. Each sequence shows a change. And millions of such observations gradually turn into one of the most detailed chronicles of the behavior of our star.
And among all these processes, there is one that shows especially well how powerful the solar atmosphere can be. These are coronal holes. Despite the name, they are not real holes in the sun. These are regions of the corona where plasma has a lower density and magnetic fields allow the solar wind to more easily enter interplanetary space. On images in some ultraviolet ranges, such regions look much darker than the surrounding corona. But this darkness does not mean the absence of activity. On the contrary, it is from such areas that the fast solar wind can originate. Streams of charged particles continuously leave the upper layers of the sun's atmosphere and spread through the entire solar system. Under normal conditions, this flow is relatively stable. But when the structure of the corona changes, so does the nature of the solar wind. And then the space between the sun and the planets becomes a continuation of the solar atmosphere.
This is one of the reasons why the boundary of the sun does not end where its visible disk ends. The star's influence extends far beyond the Earth's orbit. The solar wind moves outward. The magnetic field propagates along with the plasma. And ultimately, a huge area of space is formed, which is called the heliosphere. It surrounds the planets and is a unique shell created by the solar wind and the sun's magnetic field. Beyond it, the interstellar medium begins. And Voyager devices have already crossed the border of the heliosphere and continue to transmit data from space, where the influence of the sun becomes much weaker. An amazing connection is obtained. SDO observes the birth and movement of processes near the sun. Voyager investigates the consequences of the existence of this star at a great distance from it.
And between them is the entire solar system. One continuous chain of physical processes runs from the surface of the sun to the farthest regions of the heliosphere. And it all starts with the star's magnetic field. But even here, there are many unknowns, because the sun's magnetic field is extremely complex. His lines are constantly moving. Some structures are stable, others exist for only a few minutes. Sometimes small magnetic regions appear next to each other, interact, and disappear. Others are able to last much longer, then become sources of powerful activity. For scientists, not only the flash itself is important, it is important to understand what happened immediately before her. What changes appeared in the magnetic structure? How quickly did they happen? Where exactly did the energy accumulate? Why does one active area remains relatively calm, while the other suddenly becomes the source of the most powerful event? These are the questions that make continuous observations so valuable. If there is only one picture after the flash, part of the information is already lost. But if the telescope observed the area before, during, and after the event, it is possible to restore the sequence of changes. You can see how the system developed, how magnetic loops changed shape, how the plasma temperature changed, how the flash appeared, and how the sunny atmosphere returned to its new state. This is no longer a photograph. This is a recording of a physical process. And the higher the temporal resolution, the more details become available.
Some changes occur so quickly that human perception simply cannot notice them without accelerated or slowed down visualization. But SDO data allows us to study these processes frame by frame. And then short events become visible that would otherwise be easily missed. Small flashes, fast plasma discharges, waves propagating through the crown, sharp changes in brightness, and movement of material along magnetic lines. Each such process is part of a huge energy system. Plasma moves. The magnetic field guides it. Energy is transformed. Radiation goes into space. And part of this radiation reaches the Earth approximately 8 minutes after it leaves the surface of the sun. This means that when we observe a solar flare, we see an event that has already happened. The sun is so far away that even the light needs time to overcome the distance between the two worlds.
And if we are talking about the emission of charged particles, the situation is completely different. They need much more time, sometimes hours, sometimes days, depending on the speed and direction of movement. Therefore, observation of the sun allows not only to study its past, it helps to estimate what may happen to near-Earth space in the near future. It is here that scientific observations turn into an early warning system. When a powerful event occurs on the sun, experts analyze its characteristics. How strong was the flash? Was there a coronal mass ejection? In what direction is he moving? What is Ego's speed? What is the structure of the magnetic field inside the ejecta? The answers to these questions help to estimate the probability of an impact on the Earth. But the sun does not always warn us of a major event. Sometimes the most interesting processes have a much smaller scale.
Small changes constantly occur on the surface and in the crown. They can be almost invisible on individual frames. But if you observe the sun continuously, such events become part of the overall picture. And it is here that the huge SDO archive acquires special value. When a researcher receives data for years, he can look for patterns. What types of structures are more likely to occur before outbreaks? What changes in the magnetic field occur before instability? What processes accompany the heating of the corona? How do active areas behave throughout the entire period of their existence? Some answers are already known, but many questions remain open. And this is one of the most important features of modern solar physics. We can get images that look incredibly detailed. We can observe processes almost in real time. We can measure the temperature, movement, and radiation of the plasma. But even with this amount of data, the sun is still capable of surprising. Because this is not a simple sphere of red-hot gas. This is a huge plasma system in which magnetic fields connect processes on different scales. A small structure can be part of a much larger magnetic configuration. A local change can be the beginning of an event that will spread far into the star's atmosphere. And when STO directs its instruments to the active area, it turns out not just a bright spot in front of us. We see a node of a huge energy system. Around it, plasma moves along magnetic lines. Hot loops are formed above. Bright areas appear in some ranges. In others, there are dark structures. And everything together is constantly changing.
That is why some of the most impressive images of the sun look almost like abstract paintings. But every line and every change in brightness is related to real physics. The colors we see in such images are often conventional. They are used so that the human eye can distinguish the radiation of different ranges. Information about the temperature and state of the plasma is hidden behind each shade. Therefore, a beautiful image is simultaneously scientific data. This is a map, diagnostics, and record events. And when such images are combined into huge time sequences, the sun begins to look completely different. It no longer seems like a stationary disk. It becomes a living system that is constantly changing. New structures are emerging in some areas. On others, they disappear. The plasma rises and falls. Magnetic loops appear, bend, and break. And sometimes the whole system suddenly bursts into flames. And then it becomes especially clear how much energy is constantly hidden in the atmosphere of our star. But there is an even more large-scale process. The sun does not only create individual flares and emissions.
It passes through its own magnetic cycle. Approximately every 11 years, the level of solar activity changes from a relatively calm period to a maximum and then decreases again. At the same time, the sun's magnetic field is undergoing a much larger restructuring. The polarity of the magnetic field changes. The number of active regions increases and decreases, and the whole atmosphere of the star gradually changes its character. For SDO, this means that the observatory observes more than one sun. She observes different states of the same star. And years later, these observations become especially valuable because only long-term monitoring allows you to see the full scale of changes. What appears to be a random event one day may turn out to be part of a certain cycle several years later.
And it is here that one of the main targets of the observed SDO is located, not just to get impressive images, and understand how the star works, on which our planet depends. Because the sun determines not only light and heat on the Earth's surface, it controls the cosmic environment around us. And while mankind is building more and more complex satellites, communication systems, and navigation networks, our dependence on calm outer space is becoming more and more. Therefore,
the ability to observe the sun in the smallest details becomes increasingly important. And each new frame helps to fill another part of the huge picture. Pictures of a star that mankind has known since ancient times, but which is only now beginning to be seen for real.